Now we want to move into the last big piece of chapter 13, which is the idea of an ice table. When we're talking about equilibrium, we've talked about what it means for a system to be in equilibrium, how we can control equilibrium, but now we want to talk about how we actually predict amounts. We said at the beginning that we've used stoichiometry previously, that you have reactants and they become products, but an equilibrium description is more nuanced. It's a more realistic depiction. But how do we figure out how much products you would get at equilibrium? You have some reactants, you have some products. What does equilibrium look like from a quantitative or numerical perspective? And so this is, a really common issue we would have. And the framework that we use to solve this is called an ICE table. This is really the framework we use to set up the algebra problem to solve. And ICE is an acronym, initial, change, and equilibrium. So we're going to look through how to deal with how to set up and how to work through ICE tables. Instead of talking about it, we'll just work an example to see how this goes. Determine equilibrium concentrations if the initial concentration of HI is 0.2 molar. My reaction is H2 plus I2 becomes 2HI. Kc is equal to 3.9. Let's see how that works.
All right, so in this problem, we want to determine equilibrium concentrations based on the initial concentration of some of our species. So this is a really common problem where you've prepared a reaction mixture, you've prepared something, and you want to know what's it going to look like when it gets to equilibrium? What are all of the concentrations of all of my substances going to be? And so when we want to do this, we're always going to want to use an ICE table to set up our problem. And so we want to start by writing out the equation. Just rewrite gas plus I2 gas becomes 2HI gas. And so then we can write ICE. Sometimes you'll see these called RICE tables where the R stands for reaction. I just used I, they're the same thing. And so the I stands for initial. And so what we do is we write out the initial concentration. So we generally are going to look in the problem for those. Determine equilibrium concentrations if the initial concentration of HI is 0.2. So beneath HI, we can write 0.2. You'll note we don't have concentrations. There's nothing given for H2 or I2. That means we can assume there's 0. Basically, there's nothing given because they're not there. You prepare HI, you have your sample of HI, it's at 0.2 molar, and then you let it evolve and produce some hydrogen gas and some iodine gas. So C stands for change. Okay, so we want to know we're at our initial system. We know we're going to change in order to reach equilibrium. So our question is, what direction are we going to change? So when we're calculating or determining our change, there are two parts. First is direction. So we've talked about that. Is it a shift to products or shift to reactants? And then we also want to know the amount. And so when we look here, one of the things we can see is that there is no concentration of H2 or I2. That's the concentration of my products, or reactants, sorry, cannot decrease because that would give me a negative number, and you cannot have negative concentrations. That is not physical. Okay, that does not represent real life. So what that means is because there are zeros, and even if there's just one zero on the reactant side here, what that means is that I have to shift to this side. These concentrations have to increase. This concentration has to decrease. So we know we're going to get pluses over here and minuses over here. And it would be everything, right? It has to be split by side. Everything on the reactants has to have the same sign. Everything on the products has to have the same sign. So even if there was like some hydrogen, if there was a zero for the iodine, still got to shift to that side. All right, so that's the direction. Now we want to know amount. So we don't know how much it is, but we can say there's a variable. What we can say is we don't know how much H2 will be produced, but we could say plus X. So an unknown amount. But the thing is, because of stoichiometry, we know that if for every 2 molecules of HI that say react, because this is going to go away, you're going to make 1 molecule of H2 and 1 molecule of I2. So we know whatever amount of H2 you produce, you have to make the exact same amount of I2 because their coefficients are there. So we can use those x's and then we can take the coefficients. In this case, it is still going to be the variable x, but there's going to be a 2 in front of it. So this 2, that coefficient, shows up right there. So E stands for equilibrium. And so basically what we have at equilibrium is the combination of the initial and the change. So we start at 0, we're going to add x. So at equilibrium, the concentration will just be x, and here 0.2 minus 2x. So this is the ice table. The whole point of the ice table is it now gives us this relationship that tells us that the concentration of H2 at equilibrium is going to be x. The concentration of I2 at equilibrium is just going to be equal to x. And the concentration of HI at equilibrium would be 0.2 minus 2x. So if we knew the value for x, we could just plug it in and we get all of those equilibrium concentrations. And so the purpose of an ice table is to set up these relationships, these equilibrium concentrations relative to x. They're all related to one variable. So if I know the value of that variable, I would be good to go. So the question is, how do I solve it? And that's where Kc comes in. We know that these equilibrium concentrations are related to my equilibrium constant. I know in this case I can write its products be the concentration of HI, squared, concentration of H2, concentration of I2. And what I can do is these are concentrations at equilibrium, so are these. So I can take those expressions and plug them into here. What that then looks like is going to be Kc is equal to the concentration of HI at equilibrium is 0.2 minus 2x squared. Concentration of H2 is x, and the concentration of I2 is also x. And so this is now an algebraic expression that I can solve for. I have these variables x's. So if I know the value for Kc, again, that's a number. If I know the value for Kc, I can plug that number in and I can solve. So overall, the equation I want to be solving is 3.9 is equal to 0.2 minus 2x squared divided by x times x. All right, so Kc is given to us here. And so if you know that value for Kc, you can solve this and figure out your amounts at equilibrium. There, so let's do that. That's sorted. So I got the overall expression was Kc is concentration of HI squared, concentration H2, concentration I2. We had 3.9 is equal to 0.2 minus 2x squared, x, and x. And so what I can do is this just becomes an algebra problem at this point in time. So the ice table gets you to the algebra problem. 3.9 is equal to 0.2 minus 2x squared times x squared. I got squareds on the numerator and the denominator of this fraction. That's the same as just having the entire fraction squared. So then I'm going to take the square root of both sides, 0.2 minus 2x over x. This is equal to 1.97. I'm multiplying the x, taking the square root, multiplying the x. That's equal to 0.2 minus 2x. And keep going, add the 2x, so 3.97x is equal to 0.2. X is equal to 0.2 divided by 3.97. And I get then that x is equal to 0.05. So that's the process of working through the algebra. So we can always, the whole point of the x table is to get to the algebra, and then we do need to solve that. And so we're not quite done though, because we want to take this value for x, we want to plug it back in to these expressions that I got. The equilibrium concentration of H2 is going to be x, so that's going to be 0.05 molar. Concentration of I2 at equilibrium is going to be x, which is 0.05 molar. And the concentration of HI at equilibrium, now I do need to do a little bit, 0.2 minus 2x. So that's equal to 0.2 minus 2 times 0.05, which is equal to 0.1 molar. And again, we do just need to know that the concentrations are in molarity. The square brackets are showing us that. We want to interpret that. So these would be my desired answers, that those are the concentrations that you get at equilibrium. So technically we're done. This would be the correct answer. You can, one of the benefits of this is you can always check your work, right? You can always check your work or check your answer, because Kc is equal to the concentration of Hi squared over the concentration of H2 times the concentration of I2 at equilibrium, which are these values I just computed. So you can plug those in. I get 0.1 squared divided by 0.05 and 0.5, and I get 4. So the reference value was 3.9. So I'm not exactly the same, but you'll note I only have 1 sig fig on these. So to 1 sig fig, I got it correct. I got the right answer. With rounding, it's pretty common that you don't get it perfectly. But we're doing pretty good. So the fact that this is close to the given reference value of 3.9 implies that we probably did the right thing. Good to go. These are the actual equilibrium concentrations for this reaction.
These equilibrium concentrations are going to be really important to actually characterize chemical systems or samples that we've talked about. So, you prepared this as 0.2 Hi. You got some HI, you put it into a container, you 0.2 moles in your 1 liter container, whatever it is, and that's what you think the concentration is, right? That could be, like the sticker concentrations that you have. But because this reaction equilibrium, this reaction constant, it's product favored. 3.9 is greater than 1. This is product favored, but not by a large margin. So really, if you have a container of HI, it's really a mix of all 3 of these things. It's really only 0.1 molar HI and then the 0.05 molar of the hydrogen and the pure iodine, right? You have this mixture of that's in that container. And that's really kind of relevant, one, just in terms of, like the chemistry that you think, what you think you have as HI, also in terms of the properties. HI is an acid, it's a pretty potent one, and so we would think, we'd be careful of, say, dealing with acid safety. H2 is highly flammable, so you want to be mindful of all of a sudden what you think is just an acid, so you'd be dealing with acid safety, also has this high level of flammability. You want to be concerned with that type of safety. And so there's just ideas similar to that we want to be mindful of when we're working with any sort of sample that is potentially undergoing chemistry passively. It's not just going to stay HI, it's going to react and form this H2 and I2 as well. So these ICE tables, always the idea is you have initial, then you have the change, and then you have equilibrium. And initial, usually that information is always going to be given in the problem. Anytime that there's nothing given, you can usually assume it's 0. You may need to change your units to molarity. You could also use pressure units if you're looking at a gas system with KPs. The change has that direction of the shift. Really what we're hoping for is an absence always, if we can find an absence, because it's going to shift to that side. Otherwise, you can use Q, the reaction quotient, calculate that, figure out your direction of shift. And you can also use, then the stoichiometry side of things tells you what number goes in between the negative or positive of the x. And finally, equilibrium, you combine those two together, and that's the part that you set up to plug into your algebraic expression.
Okay, welcome to ICE tables. Participation 220 is going to be due on Friday the 20th. Week 6 homework through Saturday, and then the post lab for chemical equilibrium. So there won't be any ICE tables on there. It's all qualitative, but we will be dealing with some algebra here. Be fun. I'll see you in the next video. All more about ICE tables. See you there. Bye-bye.